Yeah, we continue with lengths, areas, and volumes, and here our focus shifts to circles and circular regions. We've been talking about in the last two videos, we talked about quadrilaterals, breezing through the ideas of rectangles, squares, parallelograms, kites, rhombuses, and of course trapeziums. So now let's talk about circles and things related to circles, circular regions. Okay, so. First of all, let's talk about circle basics, talking about things like radius, diameter, circumference, and pi. By definition, a circle is the set of all points in a plane that are the same distance from a fixed point. Of course, I mean, that's one of my best definitions of a circle. So imagine that you have a fixed point and maybe fire is burning at this fixed point, and for you to be safe from the fire, you have to be uh 3 units, I mean 3 meters away, or four, let's say 5 meters away from that fire. So that's like 1, 2, 3, 4, 5. So you have to stay 5 meters away, like that. So if you come too close, the fire burns you. So you have to stay 5 meters away from the fire. So you can stay anywhere as far as it is 5 meters away. By the time you join all the points together, that's what a circle is. So, and that's why one of the best definition of circle I know is that it is the locus of all points that are equidistant from a fixed point. So every point, you have to stay 5 meter, 5 meter, 5 meter. So in any direction, 5 meter, in any direction, 5 meter, 5 meter. So by the time you join all these locations together, you get a square. I mean, you get a circle. So a circle is the locus of points that are always equidistant from a fixed point. That's what a circle is. Okay. So, and like you have here, a circle is the set of all points in a plane that are the same distance. That's what I mean by equidistant from a fixed point. So the fixed point is called the center. Okay. So when you have in a circle, you have that fixed point about which all the points are equidistant. So this is the center of the circle. Okay. So that this is the center of the circle. That fixed point is the center. Okay, and then we have other ideas. So the constant distance from the center to any point on the circle is the radius. So you saw me having this 5 meter all the way. So that 5 meter is what you call a radius. Okay. So next we have, so key vocabulary now. We have things like radius. So the radius is the distance from the center to any point on the circle. So I mean the radius can be, so as for any line you draw from the center to any point on the circle is a radius. So the radius does not have to be in only one direction. It can be in any direction as far as it's from the circle to any part of the circle. So the diameter now is the distance across the circle through the center. Okay. So if you have a distance across the circle through the center, okay, I think I want to demonstrate that with something else. So imagine now that you have, so you move from, you move through the circle, you move from one point of the circle to the other, passing through the center. So you see, this is one radius, okay, and this is another radius, okay, but everything together, the whole line is called circumference. Circumference. So we can already see from there that circumference is the, oh, sorry, not circumference, diameter, sorry, diameter, not circumference. So that line that touches one circle, one part of the circle to another part, passing through the center is the diameter. So you can already see that the diameter is double the radius. So diameter is radius plus radius, okay? And then that is equal to diameter, okay? Maybe to make things clear, right? You have a circle, this is the center, so you have a line passing through the center to join another part, from one part of the circle passing through the center to another part. So that's called the diameter. So this is nice. This is what we call the diameter of a circle now. So, and because from here to here, you have a radius, and from here to here, it's another radius. So that's why a diameter is two times a radius, two times of radius. Okay. That's what I'm talking about. So we're back here. Then we talk about the idea of circumference. Circumference is the distance all the way around the circle. And so a circumference is more like this perimeter of a circle. You know, perimeter is distance around a circle. I mean, distance around an object. So if you have to travel around a circle, right, you'll be so imagine that you want to travel, this is a circle. So if you are traveling around this circle now, I mean, the way I'm drawing it, it's looking somehow, but it's okay. I'll try. Yeah. So this is a circle now. So if you travel around this circle, okay. So the distance around the whole circle is what you call a circumference. Circumference. So technically, it is the perimeter of the circle. So this is the circumference of a circle, and it is the perimeter of the circle. It has the formula you're going to find out pretty soon. And then we have what we call a chord. So any line joining 2 points on the circle is which the diameter is the longest chord, right? So imagine we talked about the diameter the other time. So look at this now. So we talked about the diameter the other time. So if you have a circle, imagine you have a circle like this. So um you have a circle this way. So, of course, this is the center. So, if you draw a line from any part of the circumference to another of the curve to another part, so that line, this line now is called a chord. So, by the same token, since the diameter passes through this, since the diameter touches the circle from one point to another, although it's not passes through the center, so the diameter can be seen as a special type of chord. Okay, so the diameter is a special chord. It's now a special chord. The diameter is a special chord like that. Okay. So then, relationship between diameter, radius and diameter. Of course, I showed you already that diameter is 2 times radius, meaning that radius is diameter over 2. Right. So then we talk about the idea of pi, the number pi. In fact, pi has been popularly approximated as 3.14. And interestingly, every year we have World Math Day, and it is called the Pi Day. That happens significantly on March 14, right? That's 314, March 14. So the number pi has been said to be the ratio of circumference over diameter. So circumference over diameter for any circle is pi equals c over d. Interestingly, I think somewhere in the Bible, okay, let me quickly search for that. I think I saw that as an undergraduate. There's somewhere in the Bible that tends to describe diameter like that. So let me talk about, pi, let me say pi in the Bible. I know it's somewhere in the book of Kings, pi in the Bible. Yeah, First Kings 7:23. What does it say? I particularly like, okay, he made the sea of cast metal 10 cubits from rim to rim, circular and 5 cubits high. It took a line of 30 cubits to measure around it. So can you see? 10 cubits from rim to rim is like the diameter, right? Of course, it's circular and 5 cubits high. Okay, I mean that's three-dimensional, right? But we're talking about the circular part now. So we have 10 cubits from rim to rim. It took a line of 30 cubits to measure around it. So if you imagine now. Okay, well, I mean, I want to get a more contemporary translation. First Kings, First Kings 7. I like NLT a lot this. Then I read verse 23. So, I mean, you see the Bible establishing this idea of diameter, circumference over diameter here. Verse 23 says, Then Huram cast a great round basin, so round is circle, 15 feet from rim to rim, right? 15 feet from rim to rim. That means you have the circle. So from rim to rim, we have 15 feet. Okay. So next, it says that 23, right? 15 feet from rim to rim, called the sea. Then it was 7.5 feet deep. That's talking about the height, and about 45 feet in circumference. So you see 45 feet in circumference. So that is moving around the whole thing. You know, the distance around this object now, okay, is 45 feet. So you see, this is so we see that circumference circumference. Circumference over diameter is like 40 is now 45 feet over 15 feet. That's equal to 3. And that's approximately pi right there. So that's why pi is approximately circumference over diameter. So in any translation you look at it. So you see we can the Bible uh as they inadvertently established the whole idea of pi, of the fact that the ratio of the circumference to diameter for any circle is c over d. So it is the same for all circles. So the ratio of the circumference to the diameter of any circle is that about 3 like that. So pi is c over d. So the exact value of pi is an irrational number. So you cannot nobody knows the exact value of pi, but then you can approximate it to a couple to, I mean, in some ways. So its decimal expansion never ends or repeats. It just keeps going. So we have common approximations for pi is 3.14, and which aligns with circumference over diameter, just like that thing. 45 feet over 15 feet is roughly 3. And another way we look at this, we say it's 22 over 7, which is often used for calculations. Okay. So measuring around circular objects. Now, a practical idea for measuring around circular objects will be something like this. So for an activity for class or self-study, you can collect several circular objects like a plate, like jar lid, tape roll, etc. Then for each object, you can measure the diameter with a ruler, then wrap a string around it to find the circumference. Straighten the string and measure its length. So for each object, calculate C over D. So you observe that the ratio is close to pi, which is 3.14. Okay, so you can carry out that experiment and see how that goes. So example 1, now we have a circular plate rather has radius 8 cm. So a circular plate has radius 8 cm. Find its diameter. Of course, we know that diameter is twice the radius. Then using pi, which is approximately 3.14, estimate its circumference. So the diameter is 2 times radius. So if you have radius to be 8, then the diameter is 16. Then the circumference is, of course, we know that we know that pi is like circumference over diameter. So it means that circumference itself will be pi times d. So that's 3.14 times 16, which is like 50.24 centimeters. So the circumference is approximately 50.24 centimeters. So never forget that relationship, that pi is like is roughly circumference over diameter, like that. Okay. Now we move on to 6.2, where we talk about the circumference of arc length. Okay. Now, okay, I've not talked about an arc so far, but I think this is important now. An arc is simply a portion of the circumference. So imagine that you have a circle this way. You have this circle. So the whole distance around it is a is the circumference. But you can have a portion like this. So imagine um so this is the center, right? So imagine you have this, you have this. So this portion now is a portion of the whole circumference, and it is called an arc. So in this case now we have two arcs. We have the minor arc, the smaller arc is the minor arc. We also have the major arc, which is this bigger part now. That is the major arc. And what distinguishes the two arcs is the angle. So this is the angle, big theta of the major arc, and this is the angle of the minor arc. So angles distinguish between the arcs. So an arc is a portion of the circumference, and the smaller arc, cuts out the smaller angle of the two, and the major arc cuts out the bigger angle, like that. Okay, so let's talk about arc now. So circumference formula. So for a circle with radius r and diameter d, so the circumference of a circle is given as 2 pi r. So that's another idea now, that the circumference of a circle, so circumference of a circle is given as 2 pi r. 2 pi is a whole rotation multiplied by the radius. So it's like the radius moving around the whole thing. That is 2 pi r. And of course, it's obvious that we have pi times 2r, because 2r looks familiar. It looks like the diameter. So that means this is pi times the diameter. So the circumference of a circle is 2 pi r, or if you like, you can call it pi d. So it's the same thing. 2 pi r or pi d gives you the circumference of a circle, like that. So remember that d is 2r, so the two formulas are equivalent. 2 pi r or pi d, you have the same. So example 1 and 2 now. So for example 1, find the circumference of a circle with radius 5 cm, leaving your answer in terms of pi. Okay, so circumference is simply 2 pi r. That's 2 pi times 5. That's 10 pi cm. Of course, if you have to break it down, you could have said 10 times 22 over 7, and you'd have got 220 over 7 and all that. Then the exact answer is 10 pi cm. So example, to find the circumference of a circle with diameter d is 14 cm. So you don't have to find the radius in this case. Using pi is 22 over 7 in this case as suggested. So circumference is pi d, that's 22 over 7 times 14. 7 and 14 is 2. 2 times 22, that's 44 centimeters. Now, that is that. Now, we're talking about an arc length, right? How do you find the length of an arc of a circle? So an arc is a part of the circumference of a circle. So for a circle with radius r and central angle theta degrees, the arc length is L, which is theta over 360 degrees times 2 pi r. That is for the minor arc now. So you have special cases. If theta is 360 degrees, then the length is 2 pi r. That's the whole circumference. But if theta is 180 degrees, the length is a semicircle. So see what we are saying here. So we know that the whole thing is the circumference, right? I think I don't have a problem drawing it over and over again. So you have the whole thing as the circumference. This is the center, okay? So if you cut this part out, so this angle theta now. So since this theta is proportional to the whole total angle is 360 degrees. So so if this is, let's say this is L1, the length of the small arc. So let's say this is theta 1 for the small angle, and this is theta 2 for the big angle. So, and then the length L2 is for the big arc. So we can say length, length of minor arc, length of minor arc. That's the arc with the smaller angle. That's theta 1 over 360 degrees. So it's like a proportional. That theta 1 over 360 degrees times 2 pi r. That's the circumference. So it means because of this small angle now, this small arc, okay, is taking theta over 360 portions out of 2 pi r. On the other hand, we have length of the major arc. Length of major arc. So length of major arc now will be the bigger angle, that's theta 2 over 360 degrees times 2 pi r. So on the other hand, what if the arc is something like this? So we have our circle and this angle here, and we have a semicircle like this. You have a line passing through this. So, and now you need, this length 1 is equal to length 2 now. So this is L1, L2. Okay, L1, L2. Why? Because angle on a straight line is 180 degrees. I think we saw that in a previous video. This is also 180 degrees. So we see here that L1 is equal to L2. That is simply equal to 1 over 180 degrees over 360 degrees times 2 pi r. So that means we have 1 over 2 times 2 pi r. So ultimately this is pi r. So it means that the length of a of the circumference formed by the length of the arc formed by half of the circle is actually pi r, because this total circumference is 2 pi r. So just divide by 2. Okay, that's 180 degrees. So that's basically the concept we are seeing here. So length is pi r, that's for a semicircle. So let's look at example 3. Find the length of the arc cut off by a 60-degree central angle in a circle of radius 7 centimeter using pi is 22 over 7. So the length in that case is theta over 360 degrees times 2 pi r. Theta we know is 60, that's 60 over 360 times 2 times 22 over 7 times 7. 7 cancels 7. Then we have 60 over 360 is 1 over 6. Then we have 2 times 22 over 7. Everything is 44. So we have 1 over 6 times 44. That's 44 over 6 or 22 over 3 cm, which is approximately 7.33 centimeters, like that. And for example 4, a circular track has radius 20 meters. So now this is something practical now. You have a track, a track that you can run around. They say a circular track has radius 20 meters. A runner runs along an arc of 90 degrees. Okay. So, I mean, this is the idea here now. You have a circular track and somebody runs, this is 90 degrees. So somebody runs across this arc now. Call it L, right? So this is 90 degrees. Um, so what are the other information? So find the length of this arc and how many such arcs make one full lap. Okay. So, I mean, well, not to even waste time, right? Um, so the circular track has radius 20 meters already. So we can just use this. So the length of that arc would just be 90 degrees over 360 degrees times 2 pi r. That's 2 times 22 over 7. And the radius is 20. So you can just resolve this and you get your result, which we have here already. So that's 90 over 360 times 2 pi times 20. That's 1 over 4 times 40 pi, which is 10 pi meters. So using pi, approximately 3.142. The length now, so if pi is approximately 3.142, the length is 31.4 meters. So a full circle is 360 degrees. So each arc is 90 degrees. So number of arcs in one full lap would be 360 over 90, which is 4. So there are 4 such arcs making one full lap, right? So that's easy peasy. So let's have the area of a circle, an intuition formula now. So, we've talked about the things like arc and everything. So the distance around a circle is called the circumference, which is technically the perimeter of the circle. And don't forget, our topic is about lengths, areas, and volumes. So, a perimeter is like a length round the circle. That's the circumference in this case. Then, how about when we talk about the area of a circle? Let's look at an intuitive formula here. So, intuition behind the area formula, the idea is cut the circle into many equal sectors, like pizza slices, then rearrange them alternately to form a shape that looks like a parallelogram or rectangle. Approximately, you see that the dimensions of this shape, the height is like the radius, and the base is like half of the circumference, which is 1 over 2 times 2 pi r. So the area of the circle is approximately pi r times r, which is pi r squared. So what this is simply telling us is that, to demonstrate the area of a circle, it's like you have this circle, then this is the center. Imagine that it's a pizza, and you just cut it into several parts like that, several parts like this. And then having cut it into several parts, you now cut it out and then you now stack things up. So you have say so you can stack them on themselves. So you see each one is looking like uh something like this. Imagine you have something like this, and then you arrange another part here. You have something like this. Uh, so now we have okay, like next one, I now want to stack it up. You have this and you have this. So this one now, you have this and something like this, and you keep arranging like that. So you have this coming and this like this. You have this coming and this like this. You have uh you have this coming and you have this, and it just goes on like that. So technically you can see that um the height will be like the radius, while everything you have here is like a semicircle where you have pi r, so that the area of a circle is pi r squared. Okay, so that's like of course that's base times height now, so that's base times height. So because it's now looking like a rectangle, so the base now is pi r and the height is r, and that is equal to pi r squared. That's the intuitive way of looking for the area of a circle. That's how that came about. Okay. So that's what we have here. So the area of the circle is approximately pi r. So again, cut a circle into many equal sectors like pizza slices. Rearrange them alternately to form a shape that looks like a parallelogram or rectangle, just like you have right here. Okay. So so you have arcs going like that, like semicircles, not the full thing. So and ultimately, you have half times 2 pi r now, half of the circumference, which is 1 over 2 times 2 pi r. And ultimately, the area of the circle is approximately pi r squared. So as the number of slices increases, this approximate becomes exact. So A is equal to pi r squared ultimately. So area formula for a circle. So for a circle with Okay. For a circle, so for a circle with radius r, area is pi r squared. So if we know the diameter d, so r now is d over 2 and a is pi d over 2. So I mean, since we know the area of a circle to be pi r squared now, we also sometimes all the information you have is about the diameter. So area of circle, we're talking about circle, that's pi r squared. And we know that we can say this is pi, that r is diameter over 2. If we square that, so that means pi d squared all over 4. Okay, so that's another way. So area can actually be pi r squared or same as pi d squared over 4. So whatever you have, you can always get your area in terms of the radius or the diameter. Okay, so example 1 now. So find the area of a circle of radius 7 cm. Leave your answer in terms of pi. Then approximate using pi to be 22 over 7. So the exact from the area is pi r squared. That's pi times 7 squared. That's 49 pi cm squared. The approximate, if you want to use pi to be 22 over 7. So that's 22 over 7 times 49, which is 7 goes in 49. That's 7. That's 154 centimeters squared. Example 2. A circular garden has diameter 10 meters. Find its area using pi is 3.14. So radius is d over 2, that's 10 over 2, 5, which is equal to 5 meter. So area is pi r squared, that's 3.14 times 5 squared, that's 3.14 times 25, which is 78.5 meters squared. So the garden covers about 78.5 meters squared. Or you can just say pi d squared over 4. That's pi times 3.14 times 3.14 over 4. And you also get the same result. So you can also have a reverse area problem, talking about the area of a circle. So the area of a circle plate is 3.314 centimeters squared. Find its radius using pi is 3.14. So the solution, A is pi r squared. So r squared now is A over pi, because we're looking for area of radius for radius. So the area is 314, then the pi is 3.14 approximately. So if you divide that, that's 100. So r itself now is square root of 100, which is 10 centimeters. So the radius of the plate is 10 cm. So you can have the area and then you're looking for the radius or something. Now we can talk about sectors and segments. So, we are talking about area now. When we talked about length, under length of circles, maybe I can summarize that. Lengths related to circles, right? Length related to circles. Okay, it's to circles. Length related to circles. So you remember we talked about the first length we talked about was the radius. Then we talked about diameter. Then another length related to a circle is what you can call a chord. Okay, we have chord. Then, I mean, I didn't bother talking about the length of the chord because I think we're going to see it somehow. Then number 4, we also have the circumference. It's a kind of length, right? It's a kind of length. And from the circumference, we talk about the idea of arc. So now we want to talk about areas. Areas related to circles. We are talking about, so now areas related to circles, related to circles. So the deal is we have the circle itself, okay? We have the circle itself, and now we have other things like sectors, we have segments, okay? These are like some key things we have when it comes to the area. That's the plane shape now. Now let's dig into this. We already know the area of a circle is pi r squared, or if you like, pi d squared over 4. Anyhow, so if you like. So let's look at other ideas like sectors and segments. So first of all, sector of a circle. A sector is a slice of a circle formed by two radii and the arc between them. So for a circle with radius r and central angle theta, the area of the sector is, so just like okay, I mean, let's even see it so you can know what exactly we're talking about. The other time we talked about arc, so it is the same logic that an arc is a slice of the circumference, while a sector is a slice of the area of a circle. So imagine you have your circle this way, this is the center. So drop a radius here, drop another radius here. This is the arc. We're talking about length. But now, if this is your angle theta, so this region now, this particular region is the sector. So this is a sector. But interestingly, there are two sectors. So if this is theta 1 and this is theta 2, this is theta 2. So the one with the smaller angle is the minor sector, while this other one, this whole region, is the major sector. Okay, and each of them can have their formulas. Since they are segments of the area, not of, it was the arc was a segment of the circumference, but now this whole portion is a segment of the area. So the area area of minor sector, for instance, area of minor sector can then be the angle theta 1 all over 360 degrees. That's a portion of the area pi r squared. Whereas for the major sector, the area would be the big angle theta 2 over 360 degrees times pi r squared. That's a portion of the whole area. So arc is a length, is a portion of circumference, while sector is a portion of the area of the circle. So having understood that, a sector is a slice of a circle formed by two radii and the arc between them. So you see, this is a radius, this is a radius, and this is the arc between them. So you have this. So in the same way, this is one radius, this is one radius, and this is arc between them for the major part of it now. So area of the sector will just be theta over 360 degrees times pi r squared. Then arc length of the sector, we did arc length before, that's theta over 360 times 2 pi r. So we have that before. Um, so if you're looking for the area of a sector, that's it right there. So imagine example 1 now. Find the area of a sector with central angle 90 degrees in a circle of radius 7 cm using pi to be 22 over 7. So the area of a sector is the angle it cuts out, that's 90 over 360 times pi r squared. So the area of a sector is 1 over 4, 90 over 360 is 1 quarter times 22 over 7 times 7 squared. So 22 over 7 times 7 squared is 7 goes in 49. That's 154. 1 over 4 of that is 77 over 2. That's 38.5 centimeters squared, like that. So that's for a sector. So for example 2, in a circle of radius 10 centimeter, find the arc length of a sector with central angle 72 degrees using pi is 3.142. Again, length of arc, we've done that before. That's 72 over 360. Now, length of arc is a portion of the circumference. So you'd multiply by circumference, but length of sector is a portion of the area, so multiply by area. Don't ever forget that. So because the arc is a line segment, whereas the sector is a portion of the area. So don't ever forget. So here we multiply by that. So we have 72 over 360 is 1 over 5 times 2 times 3.14 times 10. So you have 12.56 centimeters. Now, another thing we want to talk about is the circle segment. So basically, a segment of a circle is the region between a chord and the arc above it. So look at this now. So this is we've talked about sector right there. So let's talk about segment. So this is the center still. So imagine you have this chord. So this region now is what you call a segment. So this will be, because it is a smaller segment, this is what you can call the minor segment. Because this other part, so this whole part now, this bigger part, is your major segment. So you see, for a circle now, you always have that minor and major thing. Major arc, minor arc, major segment, major sector, minor sector. So this shaded region now is what you can call the major segment. Okay. So, and of course, just the way they are, we can actually find their areas too. We can find the areas. So here you have that. So see this. A segment is a circle rather, is the region between a chord and the arc above it. So you have, this is the chord and this is the arc above it. So this area, the mark out, is what we call a segment, like that. And that is what we want to talk about next. And you see, if you look at it at first sight, there may not be a clear-cut way to reach that, but we can always find a solution when it comes to math. So a common method is the area of a segment is area of sector minus area of triangle. This works when the central angle and radius are known, and the triangle is easy to handle, especially if it is often isosceles because you have two radii there. So let's look at this now. Area of segment is area of sector minus area of triangle. So let's consider you have this triangle. You have this circle. I guess I want to change. You have this circle now. and you have this segment right here. Okay, you have the segment, and this is the center of the circle, right? So, and we are interested in the area of this segment, defined by this chord and the arc above it. So what we then do is so we can think in terms of, we can now think in terms of how the chord is connected to the center. This is an angle theta right here now. So you see that this chord now, you see that this chord, I mean the segment rather, the segment and the triangle added together cut out a sector. Okay. So what we're saying in short here is that uh we have a sector cut out by that theta. So we see that area of, okay, if you can even name the sector. So if this is A, B, C, area of sector A, B, C is equal to area of triangle ABC. So you see this is triangle ABC right here. This is triangle ABC. Okay. Then plus area of segment ABC. Everything is ABC, by the way. No, or the segment will be segment BC now, because the A is not part of that. So segment BC. Okay. So this area plus this area gives the area of the whole sector. So it means that at the end of the day, we see that the area of segment, is simply the same thing as area of sector minus area of triangle, area of triangle. Very important. So that idea can help us. So find the area of the sector, find the area of the triangle, subtract the area of the triangle from the area of the sector, and it makes sense. So if you find the whole area of this whole sector, then subtract the area of this triangle, then you get the area of this segment, because the area of sector plus, I mean, the area of segment plus area of triangle gives you the area of the sector. So let's see how that plays out as we move on the notes. So here, imagine that so things get a bit messy. So in a circle of radius 6 cm, a chord subtends a central angle of 60 degrees. Find the area of the minor segment. So the minor segment, like I said the other time, is there are two segments here now. So this is the minor segment right here. The bigger segment is this whole part now, this other part, but that's not our interest. So we are looking for this minor segment right here. Okay. So want to find the area of the minor segment. That means that this theta now is like 60 degrees, right? And then we also have the radius. Do we have the radius? The radius is 6 centimeters. So you have radius is 6 centimeters. So you can see this is an isosceles triangle by automatically, because this is radius. So isosceles triangle and the angle in between. So we can easily use the idea of area like that we found before, because the angle is included. So that's half times 6 times 6 sine 60 degrees. That will give us the area of the triangle. And then the area of the sector is easy. That's 60 times 3, 60 over 360 degrees times pi r squared. It's a portion of the area. Then if you subtract the two of them, you get the area of the segment easily. So let's move. So area of the sector is 60 over 360 times pi r squared. That's 1 over 6. 60 over 360 is 1 over 6 times 3.14 times 6 squared. So that's 1 over 6 times 3.14 times 36. If you multiply that out, you get 18.84 centimeters squared. That's the area of the sector, which is the bigger portion. So the area of the triangle, like I told you, so the triangle formed by two radii and the chord is isosceles with side 6, 6 and the chord. So you see this side 6 and side 6 and this chord now. And then we have the angle in between them. So that makes life pretty easy. So once you have two sides and the angle in between, you can use this. So angle at the center is 60 degrees. So the area of triangle is now half times radius sine theta. That's the angle in between. So 1 over 2 r squared sine theta with sine 60 degrees is 0.866. So you say half times r squared, that's 6 times 6 times 0.866. So that's half times 36 times 0.866, which is approximately 15.59 centimeters squared. So with that in place now, we know that the area of minor segment would be sector, area of sector minus area of triangle. That's 18.84 that we got here minus 15.5 now, which is 3.25 centimeters squared. So in that case, the area of this place can now be said to be 3.25 centimeters squared, based on this information we have. So, and if you find the area of this minor segment to be 3.25 centimeters squared, just subtract this 3.25 from the area of the whole circle, and you will get the area of the major segment. So that it's pretty goes on like that, you know. So let's talk about annuli and shaded circular regions. So sometimes uh you have some kind of rings, circular rings, and you also want to find the area. Maybe some parts are cut out and things like that. So that's what the idea of annuli and shaded circular region. So annuli and shaded circular region. So for annulus, you have ring between two circles. So an annulus is the region between two concentric circles, and they have the same center. So you have an outer radius R and you have an inner radius R. So the area of the annulus is usually pi r squared minus pi r squared, which is pi into r squared minus r squared. So I think I need to demonstrate that. So it is the region between two concentric circles. So two concentric circles have the same center. That's what the idea is. So imagine you have a circle, then you have another circle. So, and then they have a common center. So this one has a radius small r, and this one has a radius big R. Okay. So, but the region you're actually talking about, the region we need is this annulus. So it is the region between two concentric circles. So how do you find the area of this one now? So it's simply, so area, this middle part is cut out, right? So that's simply, the area is simply area of the big circle, that's pi r squared, minus area of small circle, that's pi r, small r squared now. So that's simply pi into r squared minus r squared. And I mean, if you followed my playlist on polynomials, you can check that out, polynomial equation. This is difference of two squares. So you have pi into big R minus small r into big R plus small r. So that is the area of that annulus like that. So with this, we can easily deal with any question, any annulus like that. We can deal with annuli, like this pi into big R squared minus small r squared. So look at this now. So a circular path is formed around a circular garden, right? So the inner radius is 5 meter and the outer radius is 7 meter. Find the area of the path. Use pi to be 3.14. So R is 5 meter, big R, small r is 5 meter, big R is 7 meter. So the area of the path will be pi r squared minus pi big R squared minus pi small r squared. That's pi into r squared minus r squared. So the area of the path is pi into 7 squared minus 5 squared. That's pi into 49 minus 25. That's 7 squared is 49, 5 squared is 25. So 49 minus 25 is 24. So the area of the path is 24 pi. So if you want to approximate, so you have the area of the path is approximately 24 times 3.14, which is 75.36 meters squared. So that's dealing with annulus, that you have a ring between two circles, like as shown by this region I've shaded right here. So let's talk about shaded circular regions for common patterns now. So here we see that a in this case we're talking about common shaded region questions involving circles. Shaded parts inside the big circle, but outside a smaller circle, which is annulus. So shaded parts formed by overlapping shapes, e.g., circle inside a square, right? Then shaded parts, you can also have shaded quarter circles, semicircles, and so on and so forth. So you can have all kinds of case here. So like imagine you have a square. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Imagine you have a square and then you have a circle inscribed in it. So maybe you are interested in this region now. Of course, the way to go is you find the area of the square and you find the area of the circle and subtract the area of the circle from the square. So here now you have area of shaded region. Area of shaded region is just simply going to be area of square, all right, minus area of circle, basically. And area of square, if this is length, breadth, and this one simply has this radius. So that's area of square is length times breadth minus area of circle, that's pi r squared. So you have your area given like this, length times breadth minus pi r squared, easily. So it all depends on whatever you want. And for the annulus, we already did that the other time. So you can have shaded quarter circles, semicircles, and so on. So the typical strategy is identify the larger area, just like identify that square, subtract the unshaded area, that just like the this circle in between that is not shaded, this circle inside there, then subtract, right? So subtract the unshaded area. So use circle formulas and if needed, rectangular square formulas, just like I did up there. Okay. Oh, okay. That was a square, right? So what I had there was a square, but it would have still worked, right? So if the square has length L, so we don't even need to bother. This is just length squared minus pi r squared. But if it was a rectangle, that would be length times breadth minus pi r squared. So all works. So let's look at example 2 now that talks about this kind of concept. So a circular lawn of radius 14 meter is surrounded by a path of 2 meters. Okay. Find the area of the path. Use pi is 22/7. So the lawn radius is 14 meter. Outer radius, lawn plus path is 14.2. Okay. So so you know everything together is 16 meters. So you can then use pi into r squared minus pi r squared. So you do all of that, you get 188.57 meters squared. Example 3 tells us something again. Example 3 now. So you have a square of side 10 centimeter has an inscribed circle. The circle touches all four sides. Okay, the circle touches all four sides. So uh, the square is shaded and the circle is unshaded. Okay, so find the area of the shaded region. So area of square, of course, we know that's 10 square, which is 100 centimeters squared. Then radius of circle is diameter of circle. So diameter of circle, that's the diameter of circle is 10 centimeters because we are told that the circle is inscribed inside the square. Okay, I think I need to demonstrate what that might look like. So you have, okay, I guess I have to do the square thing now. 1, 2, 3, 4, right? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Right. Yeah. So you have a square inscribed. Now things become a bit okay, you have something like this now. So you see the radius now is the diameter of this circle now is so the length of the circle, this is square by the way. So this is the length of the square and this is the circle, right? So you see that the diameter of this circle is also is equal to the length because it touches all the sides. So now what do we have again? What's the information? We say that a square of side 10 centimeters. Okay, the side is 10 cm. So we have established that because the circle touches all the sides, right? The diameter of the circle is also 10 cm, and that makes sense. Okay. Right. So has an inscribed circle. The square is shaded and the circle is unshaded. So the square is shaded. So it's like we have the shaded region. All this shaded. Sorry, I didn't. I should hardly get a perfect job of these things. Well, you know what I'm talking about. So the question is, we need to find the square is unshaded and the circle is shaded. Find the area of the shaded region. So of course, the area of the shaded region is going to be the area of the square. So area of shaded region. Or better still, I think it's better to not waste time. Area shaded area. Okay, I was gonna do that. Shaded area is equal to area. Let me just say square area, right? Square area minus circle area, easily. Circle area. So square area is just for the square now, you have L squared. Circle area, the diameter of the circle is L, right? So in that case, now that's just pi L squared over 4, easily. So here I can even factorize L squared. So I have L squared into 1 minus pi over 4. Okay, so that's L squared into LCM is 4 now. So that's 4 minus pi all over 4. So L is 10 squared into 4 minus 3.14 all over 4. So that's 100 multiplied by 4 minus 3.14 should be like 0.86, I think. 0.86, I believe, over 4. I hope that's correct, by the way. I think so, though. Yeah. 0.86 will give us 4. Correct. So that's 100 times 0.2, right? 4 in 8 is 2. 4 in 6 is 1. Then we have 2. 4 in 20 is 215. That's like multiply by 100. That's 21.5. We're talking about centimeter squared now. So that's 21.5 centimeters squared. I believe that's correct. Yeah. I mean, I've used another approach entirely, which is fine. I mean, the way I went about it, but the basic idea is just that we are subtracting the area of the circle from the area of the square. So area of square is 100 squared, 100 centimeters squared. Diameter of circle is side of square, 10 centimeter. Radius is 10 over 5 centimeter. In my case, I just use the radius directly. So area of circle is now by r squared. That's 3.14 times 5 squared. That's 3.14 times 10, which is 78.5 centimeters squared. Shaded area now is area of square minus area of circle. That's 100 minus 78.5, which is 21.5 centimeters squared. Exactly what I got using my going this way. So, I mean, that buttresses the fact that it's actually 21.5 centimeters squared. Different, slightly different approaches, same answer. So that gives us some confidence that we are good. So now we can also talk about circle geometry in the coordinate plane. I mean, I have a playlist on coordinate geometry. Let me even show you that. And there I talked about circles. I talked about circles in that realm. So here I'm just going to breeze over it. I won't go in depth because if you want to learn more about that, you could just check that out. Where I talked about circle geometry. So I have I think, yeah, right here, circle geometry. So I think I have a couple of videos on circles altogether. So let's see. Think, yeah, see circles. So I have, first of all, circle standard equations right here, and then we have tangents and chords. I need to skip this. Okay, good. So see the whole thing about circle now. So tangents and chords, then applications of circles and things like that. So you want to check that out if you are so interested in that. But here I'm just going to breeze through it since that playlist has taken care of all the big issues, right? So circle geometry in the coordinate plane. So equation of a circle in coordinates. If a circle has center A, B, and radius R, then any point x, y on the circle satisfies x minus a squared plus y minus b squared equals r squared. So you have a special case where the circle passes through the origin. So A and B will be 0, 0. So you have x squared plus y squared equals r squared. So to find radius from coordinates, of course, from here, and I just know radius is square root of this whole thing. So square root of x1 minus a all squared plus y1 minus b all squared. So once r is known, we can then write the equation of the circle and find its area, which is pi r squared, and find its circumference, which is 2 pi r easily. So take an example. A circle has center 3, comma minus 1, passes through the point 7, 1. Find its radius, write its equation, find its area in terms of pi. So of course the radius is going to be square root of x minus a, that's AB now. That's the center, and this is x1, y1. So 7 minus 3 squared plus 1 minus minus 2 all squared. So r is square root of 4 squared plus 3 squared. That's square root of 16 plus 9, which is square root of 25, which is 5. So the equation now is x minus 3 squared plus y plus 2 squared equals the radius, which is 25. So the area is pi r squared, which is pi times 25, and you have 25 pi easily. So you can also use 22 over 7 or 3.14 if you want to go further. So example 2 here. For example 2, you have a circle. A circle has equation x squared plus y squared equals 36. That means it passes through the center. Find its radius. Of course, the radius will just be 6 because this is x squared plus y squared equals r squared. So r is equal to 6 easily. Find the circumference. Once you know r, every other thing is easy. So r squared is 36, so r is 6. Circumference is 2 pi r. That's 12 pi. Area is pi r squared. That's pi times 36. That's 36 pi easily. And then with that, we have the practice questions. First question, you have that a bicycle will have diameter 70 cm. Find its radius. Of course, the radius is 70 over 2, which is 35 cm. Then its approximate circumference, find its approximate circumference. That's 2 pi r or pi d. So that's 70 times 3.14, and you get your answer. A circular radial circumference, 31.4 cm, estimate its diameter. So we know that the relationship between circumference and diameter is pi. So we say pi is equal to circumference over diameter. So it means that so pi is circumference over diameter. So it means that diameter is circumference over pi. So that's 31.4 over 3.14. That's roughly 10, I think. To find the circumference of a circle with radius this, diameter that, you know how to do that already. Circumference is 2 pi r, or pi d, basically. So a circle has radius 14, so you find the length of an arc that corresponds to 45 degrees. Easily, that's 45 over 360 degrees, because we are talking about an arc length now. So 45 over 360 degrees times 2 times 14 times 2 times 22 over 7 times 14, and you simplify that out and you're good. Then for looking from 5, now find the area of a circle of radius 4 cm to 12 cm. Of course, area is pi r squared. So that's 22 over 7 times 4, times 4. Then 22 over 7 times 12 times 12 for this one. A circular feeder's radius 21 meters. Use pi to be 22 over 7 to find its area. Pi r squared, that's 22 over 7 times 21 times 21. And you go your way. The area of a circular plate is 78.5 meters squared. Use pi to estimate its radius. Of course, area is pi r squared. So it means that radius squared is area over pi, and then you divide and take square roots and you're good. So, the area of a circular plate is okay. We've talked about that. A circle has radius 14 cm. Find the area and arc length of a sector with central angle. This. So for that sector, now the area of the sector is 45 over 360 times pi r squared for the area. For the arc length, it is 45 over 360 degrees times 2 pi r for the arc length. Same for this now, it's 120 over 360 times pi r squared for the area of the sector. And for the length, arc length, that will be 120 over 360 times 2 pi r. Pi is 22 over 7. Then you have 7. You have number 9. In a circle of radius 10 cm, a chord subtends an angle, a central angle of 90 degrees. Find the area of the sector. Of course, that's 90 over 360 times 2. Sector now, that's area. So 90 over 360 times pi r squared, that's 22 over 7 times 10 times 10. So if the triangle formed is a right-angled isosceles triangle, estimate the area of the minor segment. So find the area, you found the area of the sector. Then this one now, the radius is 10, right? So you have half times 10 times 10, sine 90, right? Sine 90 is that 0? Sine 90 should be 0, I think. Yeah, something like that. Okay. So it says if the triangle formed is a right angle triangle, isosceles triangle, so you can work that out. So an annulus has inner radius 8 and outer radius 10. Find its area in the exact form using pi now. That's simply pi into 10 squared minus 8 squared. That's pi into 100 minus 64. That's 36 pi easily. Using pi now, you have 36 times 3.14. You're good to go. Then 11. So a circular pond of radius 6 cm is surrounded by a path of 3 meters. So find the area of the path. Okay. So a pond of radius 6 cm. So the pond itself has radius 6 cm. And then you now have a path around it. Okay. Now have a path around it of say 3 meters. Have a path around it of 3 meters, right? So you see the big radius r is 9 meters and the small radius r is this. So area of path is simply going to be pi into r squared minus r squared. That's 22 over 7 if you like, into r squared. That's 9 squared minus 6 squared. So that's 22 over 7 into 49 minus 36. That is 22 over 7 times 13 meters squared. So you just simplify that and you get your results like that. So yeah, all of that will go. So then we have the whole so it says the area of the path, of course, that's what we found here. The total area, pond plus path. So in that case, now that'll be pi big R squared plus pi small r squared. So that's easy to handle. Then for question 12, a semicircle of radius 7 cm is drawn on one side of a rectangle of length. I mean, you can figure all of this out. So work at this. So thank you so much for listening. This is the end of this video on circles and circular regions. It's been an interesting ride. So everything circle you can get from this video. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Okay. If you have subscribed already, I thank you very much. If you haven't subscribed, go ahead and subscribe, please, and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can click on join also if you want to become a member of the channel, and that gives you some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have here. Till I come your way again, keep doing maths right. Bye.